This is a pre-assessment working on sections 3.1 through 3.3. So we're going to go over all of the concepts and the ideas that are going to be assessed from this first half of chapter 3 dealing with functions. So the first thing it says, determine whether the relation is a function. Explain your reasoning. So we know that functions, definition of a function is for every input or x value, it has one unique output. So when you input 3, and you get 6, the next time you input 3, you would expect to get 6. And question number 1 shows a great example of data not mirroring a function. And the reason is because of this very problem, is when you input 3, the output was 5, and then when you input 3 again, this time the output was 8. And that is not consistent. That is not unique. That is not one unique output. That is multiple outputs. So if it produces multiple or different outputs each time you input the same input, that would be not a function, because you have 2 different outputs for one input. Here's a different, so each of these examples are going to be in different data formats. So we're always going to look at our input. So 0, 2, 4, and 6. I don't care about the output until I see a double or the same input. So I'm just focusing on the input first, and I don't see a repeat of an input. So at this point, I know that it is a function from the data presented. If we go back, we're looking at our inputs, And when I'm looking at my inputs, I notice, oh, I have the same input. So when I have the same input, I now look at the output. That's the only time I look at the output. And I notice here in this situation that the outputs are different, so that's why I'm making that decision that it's not a function. Here, I don't repeat, so I don't have to look at the output. I'm not concerned about the output because no input ever repeats. Here's a question some students ask. What if you have this, Mr. Mack? Is this a function? So I'm looking at the input, I'm looking at the input, I'm looking at the input, I look at the input, and I notice my input repeats. So now I need to look at my output. And since the output stayed the same, it wasn't different, this is a function. So it's not that it can't repeat, it's just if it does repeat, it better produce the same output. So very interesting question there. I'm looking at the input, goes to one output. This input goes to one output. This input goes to one output. So that would be a function. That is an example of a function. Create an input-output table or mapping diagram that shows a relation that is a function. So we can do XY, I can do numbers, and I can do 5, 6, 7, 8, and this is a function. My X values do not repeat, so I do not have an input that has 2 different outputs. Identify the domain and range of the graph and determine whether the relation is a function. So first of all, let's do the domain. this is a continuous graph, so I need to use a inequality or a compound inequality and inequality, or I need to describe. So my x values, what x values do I plug in this graph? I'm going to plug in all real numbers. Every single number is an input for my x, my domain, which represents the x values. So if I took all the points and all the coordinates and I wrote down all of the coordinates for every single point, and there are an infinite number of points, but if I wrote them all out and looked at the inputs, the x values, I would know that I used every single value for x. Every single number in the number system that I can think of is a value that gets input into this graph to create this graph. Because this goes on forever and it's going to go towards negative infinity. This goes on forever and that goes towards negative infinity. So my domain is all real numbers. Now my range has some limits because it's never going to go below here. It'll go here, it'll be a point, that is a coordinate, that is a value, that value is 0, -4. But since I'm on my range, I'm on the y-axis, what is my lowest y value? That would be this value. So my range is going to go y is greater than or equal to -4. I need that equal sign because this is a point, meaning it's a solution. This line consists of all of the solutions to the equation. I don't see the equation, but I know it represents an equation. And so this is my lowest y value. No input, no x value when I plug it in will ever produce an output lower than this. So my range, the way I write it, I would write it in a solution set and I'd write y as greater than or equal to -4. So hopefully, oh, and let's go back. Is it a function? Yes, it is a function. We have multiple ways to determine whether it's a function. In this example, let's use the vertical line test. So we're going to take a vertical line and we're going to drag it across the graph. Is there any point where there is one input that produces two different outputs? So what do I mean? Oh, can't delete that. Delete. So when I look at this input, the input is 2 and the output is 0. There is no other point along this input, 2. If there was another dot here, then that would mean that would be 2, -3. That means when I input 2, I got 2 different outputs, but that's not the case in here. That was an example of when it wouldn't. So this is a function. Yes, this is a function. And we can do that using that vertical line. Let's look at this next one. So let's identify the domain. So the domain deals with my x values. So what x values do I use? Well, my x values are going to be within this group, between these, because when I plug in 0 for x, I get 3 as an output. When I plug in 1, I'm going to get this y value and this y value. When I plug in 2, I get these 2 values. Input, I get 2 outputs. Input, 2 outputs. Input, and then all the infinite number of inputs between these values also. But my smallest input is going to be 0 and my largest input is going to be 6. So my domain goes from 0 to 6. That's how I would describe that solution. And then my range, what are my y values? My y values, the lowest y value is 0 and the highest y value is 6. And I have equal signs because And we're going to put y in the range. Make sure, that's where students make a mistake. They put the wrong variable in the wrong domain or range. Because this is a point. Since it's a point, that means it's a solution. So that point 3, 6, when I input 3, I got 6 for my y. So that is a solution. And so that's my highest y value. Is it a function? It is not a function. And we talked about why it wasn't a function. We gave an example because when I inputted 1, I got 2 outputs. I got this as an output and I got that as an output. So that signifies that it's not a function. Identify the domain and range of the graph and determine whether. So the domain, again, is all real numbers. In this graph, even though it looks like it goes up and it doesn't go past 4, it will. It will just continue to go. It just won't get out to positive infinity for a long time, but it'll get there. And the same thing here, we are moving towards negative infinity. We'll get there. So the domain is all real numbers and the range is also all real numbers, because we will definitely go to positive infinity and negative infinity. And that's what our range deals with our y values, our outputs. And is it a function? Yes, it is a function. There are no double points. Yes, it is a function. I think that was my question. Yep. Okay. 3-1 station 3. Identify the independent and dependent variable of the function. So independent is going to be the x. Independent is x. The dependent is going to be the y, because we're going to input the x and we produce the y. That is going to be the output. The output depends on what I plug in for x. So identify the independent dependent variable of the function. Create an input-output table to find at least 4 ordered pairs for the function. Okay, so we're going to take this equation and we're going to create a chart. That is y equals 1.25x plus 3, and it's going to produce my y, and then I have my ordered pair or my solutions, my relationship between the x and the y. I'm always going to plug in 0. 0 is the easiest. Plus 3, that's y equals 0 plus 3, y equals 3. So when I input 0, I get 3. Now let's look and talk about the reality of this. It says the function y equals 1.25x plus 3 represents the height, y, in feet of a tree after it has been alive for x years. So here's the funny one. After 0 years, the height of the tree is 3 feet. Now I know that doesn't make very much sense. We talked about that in class. That was a weird one. And notice I'm not going to put in negative numbers because I can't have negative years. X is representative of years, y is feet, height. So after 1 year, it's going to be 1.25 times 1 plus 3. Y equals 1.25 plus 3. Y equals 4.25. And we get 4.25. So the height of the tree after 1 year is 4.25 feet. Let's do year 2. Y equals 1.25 times 2 plus 3. Y equals 2.5 plus 3. Y equals 5.5. So after 2 years, the height of the tree is going to be 5.5 feet. Last one, year 3, y equals 1.25 times 3 plus 3. Y equals 3.75 plus 3, or 6. Sorry, started cheating there. 6.75, 6.75 for my height. And so year 3 is 6.75. Perfect. And put out 4 ordered pairs of the function. All right, so we just needed to find 4 solutions. 0, 1, 2, 3 would be my domain that I inputted. Those aren't the only values. You could have done 10, you could have done 20, you could have done 100. I just wanted 4 ordered pairs, any 4. I just chose the easy ones. So let's go back and see. So we know that this is the height after X years. That's how much it's growing for X number of years. This 3 is its starting height at year 0. So the tree apparently springs into 3 feet. And that's the unfortunate thing about that problem. It didn't really make complete sense. So here's our new one. It says the function y equals 3.00x minus 75 represents the profit y in dollars earned after selling X cups of Italian ice on a hot summer day. Hot summer day tonight. I think that's a Bruce Springsteen song. Okay, so independent, dependent. The independent variable is going to be X, and the dependent is going to be Y. What does X represents? X is the number of cups of Italian ice, and Y is the profit. Okay, so let's do this again. Let's input, output. Input X, Y, and then we get X, Y as our solution. Our formula is Y equals 3X minus 75. So after selling 0 cups of Italian ice, 3 times 0 minus 75 equals 0 minus 75. Y equals negative 75. So after 0 cups of Italian ice sold, I am $75 in the red, as they say, because this is the profit. So I have negative $75 of profit. I am still running my business at a deficit, as they would say. So let's change it up. Let's do 10. Let's not go 0, 1, 2, 3. We've already done that. Let's try 10. So 3, 10, 75. So 3 times 10 is 30 minus 75. Y equals 45. And so, negative 45, excuse me. Negative 45. So even after 10, selling 10 Italian ices, I'm still in the hole. I'm still in the red. I still am not making a profit yet in my business. So let's do 30 cups. Let's do Y equals 3 times 30 minus 75. That gives me 90 minus 75. That gives me 15. So after 30 cups, after I've sold 30 cups of Italian ice, I'm finally, this is not necessarily the make or break, but I am finally in the green, or in the black is what they call it. I am making money. I have a profit of $15 at that point. All right? And let's try something, because let's have my goal be, I want to sell 100 cups of Italian ice in a day. How much money would I have? 100, Mr. Mac, not 30. How much money would I have? How much profit would I have if I could sell 100 Italian ices in a day? Well, that would give me $225. So if I could sell 100 Italian ices, I would have $225 of profit. Nice. That's not too bad. Yeah, so what is this? This is the amount of revenue. This is my revenue of Italian ices, And this is my initial investment. This is how much I have to spend to start up. That's my startup cost. Yeah, that's my startup cost. It's going to cost me $75 to get the ice, to get the food coloring, to get the ice box, whatever. Those are my initial costs to start my business. And then each cup I sell, I'm charging $3 per cup. So this term would tell me how much money I'm making for my cups. And then Y is my profit, or the difference between my revenue minus my initial costs. That's a good one for all you entrepreneurs. Station 4, input-output tables worksheet. All right, this one's going to take a little bit more time because it says at least 7 inputs. Yikes. Create an input-output table of the function. Create a graph using the ordered pairs listed in your table and identify the domain and range of the function. Okay. All right, we didn't have to do that on this for ordered pairs. We didn't have to graph it. So here we go. We're going to have my X, which is my input. Here's my Y. Here are my ordered pairs. And now we need 7 of them. So I'm going to start with 0. And I got 0 squared plus 1. 0 squared is 0 plus 1 equals 1. So my first ordered pair is 0, 1. This is going to be a lot of paper. Let's do 1. Y equals 1 squared plus 1. Just making sure I did the equation right. 1 squared is 1 plus 1 is 2. So my next ordered pair is 1, 2. I'm going to do -1. When I do -1, we have to be very careful. You have to put it in parentheses because we are squaring the value that we're inputting. We have to square, we have to take this completely. That negative is attached to my input. So -1 squared is 1 plus 1 is 2. So we again get 2. So -1, 2. That's 3 values. Let's do 2. Y equals 2 squared plus 1, which equals 4 plus 1, which equals 5. So when I input 2, I get 5. Let's do -2. So we need parentheses again. So -2 squared is 4, plus 1 is 5 again. That's +5. So I get -2, +5. Let's do 3. Y equals 3 squared plus 1, which is 9 plus 1, which equals 10. Do we see the pattern? Guess what we're going to get when we plug in -3? -3 quantity squared. And because we're squaring each value, it's going to have the same output as its negative and positive. So that's going to be 10. So -3, 10. How many I got there? Do I have 7? Nice. 1, 2, 3, 4, 5, 6, 7. All right, let's get the graph in here. So let's pull up a graph and let's start graphing those points. Let's plot those points. So we have 0, 1, 0 on the X, 1 on the Y. We have 1, 2. We have -1, 2. We have 2, 5, I think it was. 2, 2, 3, 4, 5, and we have -2, 5. And then we have 3, 10, I think it was. 3, 10, 3, 10, and -3, 10. Hey, that's not too bad because it sits on my graph. And now I'm going to connect the dots and I'm going to show the rest of the values. So graph using order, create a graph. So I created the graph. Using the ordered pairs listed in my table, I'm going to identify the domain and range. So the domain is going to be all real numbers. I'm just going to keep entering in numbers towards positive and negative infinity, and there are no constraints to my inputs. We just keep going. Now there are constraints or boundaries for my range. My range, my lowest value is going to be 1. So I'm going to say y is greater than or equal to 1. Remember, we need to use y as my range variable, and I'm going to put my answers in solution sets. So y is greater than or equal to because I will get an output of 1. That's my lowest output. Every other output will be above positive 1. So that's pretty good. Very similar to it. Only difference is we're going to get bigger much faster. So if we do x, y, we can do our graph here. I don't have to show it. So when we plug in 1, we get -2. When we plug, oh, sorry. When we plug in 0, we get 0. When we plug in 1, we get -2. When we plug in -1, we still get -2. When we plug in 2, we are going to get -8. When we plug in -2, we're still going to get -8. When we plug in 3, we are going to get -18, right? Yep. And when we plug in -3, we still get -18. So those are my 7 values. I'm going to put negative, we're going upside down. Okay, so 0, 0 is a point. 0, 0, 1, -2, -1, -2. 2, -8, -2, -8. 3, -18, so 11, 12, 13, 14, 15, 16, 17, 18. And then 3, so that's going to be there. 3, -18, and -3, -18. This time, it goes like this. And we should know that. Our exponent is even, so we knew it was going to be a parabola. And then we saw that our a value was negative, so that kind of led me to believe or to understand that it was going to be upside down. So now let's talk about the domain and range. So the domain is still going to be all real numbers. We still will be able to input any number, but my range this time is going to be a little bit different. My range, what is my range, goes from 0 to -infinity. So I have to say y is less than or equal to 0. So that's how I would do 0 all the way to -infinity on my y-axis. Does it ask whether it's a function? Range of the function? No, it doesn't. It kind of alludes to that it is a function. Let's look at number 9. The equation 2x plus 1.5y equals 18 represents the number of x of book raffle tickets and the number of y of food raffle tickets. So we have book raffle tickets and food raffle tickets. You buy at a club event. Represent the situation in a table and in a coordinate plane. Does the situation represent a function? So how much does a book raffle ticket cost? It costs $2. So this is the amount in money of book raffle tickets. How much does a food raffle ticket cost? It costs $1.50. And this term represents the total amount of money that I've raised through food raffle tickets. And 18 says, hey, when does the number of book raffle tickets and the number of food raffle tickets equal 18? So that's going to be a very interesting solution. Represent the situation in a table, and let's see what we get. Okay, so there's a couple things that I want to do, that I can do. So if I want to do the situation in a table, this is the fun part. I'm still going to look at x as my input. I can still leave it in, and this is called standard form. When the x and y are on the left side and the constant is on the right side, we call that standard form. And we get this. We can still get a point. So if I have zero book raffle tickets, so I can plug in 0. What I'm now solving for is when I have zero book raffle tickets, how many food raffle tickets will I have? And we're solving this. And so we get 1.5y equals 18, divide by 1.5, divide by 1.5, and y equals, is that 6? No, is it? Yeah, why don't I want to think it's 6? Is it 6? It's not 6. There's 2 in every 3, and there are 12? Is it 12? I think it's 12. I'm sorry, I'm not using a calculator, I'm using my brain. So I'm going to say 0, 12. When we sell 0 book raffle tickets, we have to sell 12 food raffle tickets in order to raise $18. That is equivalent to the $18. Okay, now here's the, should I do this? Okay, no, we'll do this. So we'll do it 2 ways. I'll show you a little trick. So we can keep doing this. We can plug in 1 and keep solving for my food tickets. So it's 2 plus 1.5y equals 18. And then we subtract 2 and you get 1.5y equals 16. That's not going to be a clean number. That's going to be a decimal. And we need to see, actually this is good. So we need to see what this value represents. 16 divided by 1.5 is going to give me 10.6 repeating. So 10.6 repeating, or 10 2/3 raffle tickets. So 1 book ticket, raffle ticket, would equate to 10.6 repeating food raffle tickets. Now what's wrong with that answer? Well, you can't have partial. So this really isn't a solution. That's not, it would never produce that, because you can't have partial raffle tickets. It's not like you're going to pay less. These are the denominations. You can only have them in whole number denominations. So where this worked, this definitely worked, this does not. And we could keep going, and you could go, okay, let's do 2. Sorry, not in green. Let's see if 2 produces a whole number thing. What I would suggest is that you plug in 0 for y, because that would be the other extreme. So I would have this, I would use this equation still, 2x plus 1.5 instead of y, because I'm plugging in y. I'd plug in 0 into the y variable, and then I would solve it. And you get 2x equals 18, divide by 2, divide by 2, x equals 9. Now this value goes over here. So that would be the other extreme. So I know that if I buy 9 book tickets, that I would need to buy 0 food tickets in order to spend $18. I only have $18 to spend, okay? So the nice thing about this is you just found these points in the extreme, because we're going to have, what do we have? X is book raffle. So this is book, number of book raffle tickets. And this is the number of food raffle tickets, because that's the y. So if I use these points, 0, 12, well, let's move the book over. So we have 10, no, we have 10, 11, 12. So this is 0, no, duh, hello, 0, 12. Sorry, 11, 12. So this point right here, represents 0 book, 12 food. Let's make sure 0 for X, which is book, and 12 food, which is Y. And then the other extreme would be 9 book and 0 food. So that would be right here. And now you cannot drag it like that. You cannot make it continuous, This is not going to be a continuous because we have discrete raffle tickets. So I guess I do have to do a little work here. Does the situation present a function? Yes, it presents a function because we're not going to repeat any, but represent the situation in a table and in a coordinate plane. So what we would need to do, we would have to do a lot of work. 1 doesn't work. 2 will work. So this is 9, 0. Maybe it doesn't. No, 2 doesn't work. It's going to be multiples of 3. So 1, 2, 3 will have to be a value that would work. And 6 and 9. I'm pretty sure that those are the only whole number. So let's do 3 for x, which would be 6. 6 minus 18 is 9. And that is going to be 9. Is it 3, 9? 3, 9. I bet it is that value. And then we would do 6. 6 times 2 is 12. Minus 18 is 6. And is 6. 6. 6? Is that right? I don't know. I feel like I messed up. See, you want to know what the problem is I'm doing in my head. So that's not good. 1, 2, 3, 4, 5, 6. Would that make a straight line? No, that doesn't make a straight line. Mr. Mac made a mistake there. See? Stop taking shortcuts, Mr. Mac. It never works. Never works. So my equation is 2x plus 1.5y equals 18. So I'm going to plug in 3. 3, which is 6. I want to make sure. Minus 6 is 12. 12. Divide by 1.5. Divide by 1.5. Y equals 4. It's 8. Sorry. That's 8, not 9. So where's my graph? So 3 is 8. 3 is going to be 8. Better. I hope it's better. And then let's do 6. I know my inputs were correct. 2 times 6 plus 1.5y equals 18. That's 12.1.5y equals 18. Minus 12 minus 12. 1.5y equals 6. Divide by 1.5. And we get 2. So it's 4. All right, so that is 6, 4. 6, 4. 6. 1, 2, 3, 4. That looks like a straight line. Yes. Notice the slope in that too. We would not connect the dots. I almost connected the dots again. They are going to be discrete still. So let's make sure, does the situation represent a function? Yes. Represent the situation in a table and in a coordinate plane. Okay. So we need to have dots. That's the important thing. All right, that one was hard. Find the domain and range of the function. So we should be able to look at this problem and understand that we can input any x value. So there's no constraints on what we can enter in. There may be constraints on what we get out, our range. Our range may be bound. So let's check it out. Let's do a couple points. X, y equals the opposite of x plus 1, y. So if I plug in 0, I get 1. If I plug in 1, I'm going to get 0. If I plug in negative 1, I'm going to get 0. If I plug in 2, I'm going to get, if I plug in 2, I'm going to get negative 1. If I plug in negative 2, I'm going to get negative 1. Negative 1. So let's graph that, see what that graph looks like. 0, 1, 0, 1, 1, 0, negative 1, 0, 2, negative 1, negative 2, negative 1. And this is an absolute value, so it's going to look like this, and it's going to look like this. And so my domain still is all real numbers. My range is going to be, y is less than or equal to 1. Yep, because it's going to be towards negative infinity. Okay, so I think that's a question. Find the domain and range of the function. It's a good tricky one, knowing absolute values. This is so much easier. So the domain, now since it's discrete, I'm going to list my domains. So negative 2, negative 1, 0, 1, and 2 is going to be my domain. Those are my x values. My range, which are my y values, are 0, 1, and 2. I do not need to duplicate it, even though negative 2, 2 gives me that, and 2, 2 gives me that. So even though my range produces 2 twice, I'm only going to list it once. And I'm always going to put my domain and range in numerical order. Find the domain and range. Domain is going to be domain x, so negative 3. Oh, it's going to be negative 3, and notice it's continuous graph, so I need it to be, my x values are going to be greater than or equal to negative 3, but less than or equal to 2. That would be my domain along my x, because that's my x. So from here to here, so that is negative 3 to positive 2. Now, when I go to look for my range, now I'm dealing with my y. So now I'm going on my y values. So my y is going to be positive 2 and negative 2. I also should look at my increments. My increments are by 1. So my range is going to be negative 2 is less than or equal to y, which is less than or equal to 2. I have to use y because I'm talking about the range. Common mistake. Estimate the intercepts of the graph. So intercepts, we know intercepts when we talk about the x-intercept. We're talking about plugging in 0 for y. When we talk about the y-intercepts, we talk about plugging in or the x value being 0. So if I have my x-intercept, it's where the line crosses the x-axis. So where does this cross the x-axis? It crosses the x-axis right here. I'm running along the x-axis. I see where the line crosses over it. So my x-intercept is going to be my x value along the x-axis. So that I'm going to look at my increments. That is negative 2. Now when I go look for my y-intercept, I'm going to go along the y-axis and see where the line crosses over. And what y value is that? That y value is going to be negative 3. So those are my two intercepts. These are my answers. Looking at this, again, if I'm looking for my x-intercept, I'm looking along the x-axis. I guess we can go green. X-axis is negative 4. So my x-intercept is negative 4. My y-intercept, I'm looking along the y-axis, and I see that it's that increments of 1, so that is positive 4. So those are the x and y intercepts. Well, let's go back to this. Let's test it. Let's make sure, because my x-intercept, let's check. So here's one other way that we can check. When we talk about the x-intercept, that coordinate is, negative 4. That value, that point, that solution is negative 4, 0. Remember, y is always going to be 0 for x-intercept. So I can take this equation and I can plug it in. So let's plug in the values. What's my y value? 0 equals the absolute value of my x value, which is -4 plus 4. And now let's simplify. So -4 plus 4 is 0. And now I take the absolute value of 0. And so since that came out, I know that this is an intercept. I know that is the correct x-intercept. You don't have to do that, but just in case you want to check your solution. Exercise 5 and 6 approximate when the function is positive, negative, increasing, or decreasing. Here we go. All right. So positive. So let's deal with the positive first. Our positive means when are the solutions of this graph? So we're talking about this graph. When are these points? Because these points consist of solutions to this equation. So when do those points, when are they positive? Meaning when you input, when is the output positive? When is the output positive? When are the y values positive? And the y values are positive when it's above the x-axis. Reason being is because these outputs here, each of these points, let's take this point, is 0, 1. Notice the output is positive. If we pick, if we pick this point, that input is 4. What's the output? -1. So notice your output is not positive because it's below the x-axis. So we only want the points that are above the x-axis, because when you're above the x-axis, you have positive outputs or positive y's. So the way that we look at it is through the outputs, but the way we are describing the inputs. So we want the perspective of what inputs will produce positive outputs. So this is an interesting one because there's two sections. So one is x is less than 1. Why didn't I use equal? Because if I used 1, if we say 1 produces a positive output, well, let's look at that point where 1 is inputted. That point is 1, 0. Well, 0 is not positive. 0 is neutral. So I would not want an equal sign on that inequality. And because there's wings, I need 2, or when x is greater than 5, because that's my input. 5 on my x is when it gets above, and 1 on my x is when it goes above in the other direction. So that would be my positive answer. My negative, when is the graph negative? So now we're talking about when does the graph go, or when do the solutions go below the x-axis? When are my outputs negative? And this is a segment, so I'm going to use a compound inequality. And it's between 1 and 5. So I'm going to do 1 is less than x, which is less than 5. Notice I didn't use y, because I want to know what inputs. They want to know what inputs will produce negative outputs. So when my x is greater than 1 and less than 5, then those will produce negative outputs. And I'm going to write a compound inequality for that. So that would be negative. So that would give me the negative part of the function. Now the next question says, when is it increasing? When we look at the graph and we take 2 points and you look at the left point going to the right point, when is it increasing? When does the graph increase when we go left to right? That would be when it's increasing. So where does it start? It starts at 3. Don't know if you see that, why it starts at 3, because here's my bottom. This is the bottom of my graph. And at that point, it turns from going negative or decreasing to increasing. So let's do increasing. Let's create some space here. Increasing When do my outputs start increasing in series or succession? So I'm going to say that when x is greater than or equal to 3, because this is 3 at this point, 3, that point is 3 as my input, it starts increasing. I'm just going to erase that little stuff. So it's increasing when x is greater than or equal to 3, and it's decreasing. This graph is decreasing, meaning it is going, it is looking at it left to right. It is decreasing. Now this is the hard part. This is where, because I've been telling you to look left to right the whole entire time. And so, well, it is decreasing, but how do we say from numbers from negative infinity to that 3 point? So how do I get all these numbers? Well, this is the hard part, is I want values that are less than 3. Less than or equal to 3. So x is less than or equal to 3. Those are all the inputs where they go negative. That's a hard one. That definitely makes it very difficult. That's the trickiest part. All right, the last part of this is, let's talk about the end behavior. So the end behavior. So that's the ends of the graphs. So I talked about end behavior has 4 things. So when we look at end behavior, let's do this. Let's create a page. Let's bring this. When things are going, when my x, if we're going right towards positive infinity, that would be to the right on the x-axis. When I go towards negative infinity on the x-axis, that would be left on the x. When I go up towards positive infinity on the y-axis, that's going to be up. When I go down on the y-axis towards negative infinity, that would be down. So we're going to use those terms. So x towards positive infinity means right. When x moves towards negative infinity, that means left. When y moves towards positive infinity, that means up. When y moves towards negative infinity, that means down. Now, the flip side is true. When I say right, we mean x is moving towards positive infinity. When I go to the left, I'm talking about x moving towards negative infinity. So let's look at this graph. This graph is going right, this portion of the graph. So that is going to the right. So right is x moving towards positive infinity, and it's going right and up. So up would be positive infinity. So that's one of the end behaviors. Let's look at the other end behavior, this one. Well, we're going to do the x part first, so that's going to the left. So as x moves towards negative infinity, left, it also goes up. So up is positive infinity. So the end behaviors would be that. It's a good little trick. It works. So good luck with that. I hope that clicks for you. So let's look at this. It says determine whether the graph represents a linear. Was that it? We only have one of those? Wow, you got off nice and easy. Maybe we have some later on. In exercises 1 and 2, determine whether the graph represents a linear or nonlinear function. This is a linear function, and explain. Well, we can take multiple points and we can look at the rate of change. So you go up 2, right 1, up 2, right 1, up 2, right 1. It has a slope of rise or up 2. It has a run or right 1, so a slope of 2. So that's why it's linear. It has a constant rate of change is the mathematical reasoning. Okay, this is good. So we could take these points and plot them on a graph, or we can also look at the rate of change. So we're adding 1, we're adding 1, we're adding 1. Now when we look at our y's, we are adding 2, we are adding 2, we are adding 2. Now here's the thing. What is the rate of change? Remember, it is the rise, or the change, or the difference. We'll say the difference of y's. Because we just talked about y's go up and down. That's your rise. And slope is rise over run, meaning the difference of x's. So the difference, the change between the y's is positive 2. The change in x's is positive 1. And that gives me a slope of 2. So it is linear because it is a constant. So it is 2 over 1, 2 over 1, 2 over 1. That relationship between the points is constant. Good. Determine whether the equation represents a linear or nonlinear. We could plug in a bunch of inputs and look at the rate of change, or we can notice that this is written in slope-intercept form. Slope-intercept form is when y is isolated, meaning we've solved for y. And then we notice that m, which is the coefficient of x, represents the slope, and b represents the y-intercept. That doesn't really mean anything. It's really the slope that determines linear. So it has a constant rate of change of 4, meaning it will go up 4, right 1, up 4, right 1. The other thing that I've taught you is that the coefficient, not the coefficient, Mr. Mack, the exponent of x is to the first, and the exponent of y is to the first. So we know that all linear equations have an x exponent of 1 and a y exponent of 1. So this looks like it's in y equals mx plus b, but notice this. What is the exponent of x? That's x to the 1/2. We can rewrite this as y equals x to the 1/2, the square root. So the numerator is the exponent. The radical is the denominator. So since its exponent, the exponent of x is 1/2, we know that this is nonlinear. It is nonlinear because it cannot be written in slope-intercept. If we plugged in a bunch of points, let's plug in some points. Let's do that. We haven't done that before. If we plug in 0, you get 5. We plug in 1, you get 6. And now we need to plug in another one. Let's do 4. If we plug in 4, we get 7. So 0 produces 5 as an output. Input of 1 produces 6. Input of 4 produces 7. So let's look at the change. That's plus 1. This is plus 3. That is plus 1. And this is plus 1. So what is the rate of change? So remember, they have a relationship. So we see that the rise is 1 here. So the slope of this section is 1 over 1, which equals 1. But the slope of these, between these 2 points, is going to be 1 over 3, or 1/3. So that is not a constant rate of change. So it is nonlinear. Also, if we graphed it, we'd notice that it doesn't make a straight line. But that's a real good example. We didn't go over that in class. It's another way of proving that the rate of change gets different, is not constant. Good. Number 18, a taxi company charges an initial fee of $2.80 plus $3.50 per mile traveled. So if I had to create an equation, this is a good preface for you. So cost equals, well, it's $3.50 per mile plus, an initial fee of $2.80. Just getting in the taxi cost me $2.80 before I travel any distance. But once I get in the car, for every mile, I'm going to be charged $3.50. Does the situation represent a function? Yes, it does, because this is in y equals mx plus b, because my x variable, which is m in this case, has an exponent of 1, and my y, which is represented as c, has an exponent of 1. If we plug in, or if we graph this, we would get a linear. So yes, it is a function. What is the independent and dependent variables? So we know that m represents the x, so m, or miles driven, is going to be the independent, and c, cost of the ride, is going to be the dependent. The cost depends on the number of miles that I ride in the taxi. If so, identify the independent and dependent variables. We did that. You have enough money to travel at most 20 miles in the taxi. Find the domain in range. Okay, so I find the domain in range at most. Okay, so I have, it's going to cost me, that's my C, cost, or I can flip it and say, well, I only have $20. So 3.5 m plus 2.8. And we can do, we can solve for that. We can minus 2.8. We can minus 2.8. I'm thinking about this as I write. You have enough money to travel at most 20 miles in the taxi. Find the domain in range. So I can travel less than 20 miles, or I can travel up to 20 miles. Okay, so yeah, we'll do this. We'll do this. Let's stay the course. So I got to borrow. This is 19, 10, 2. That is going to be 17 equals 3.5 m. Divide by 3.5, divide by 3.5, and 17.2 divided by 3.5 gives me 4.914. 3.914. 3.9914 miles. Okay. Didn't say whether I had to drive complete miles. You have enough money to travel at most, 20 miles, Mr. Mack. I know. You were screaming at me again. You were screaming at me. I'm sorry. I'm sorry. I plugged it in for C, not M. Sorry. C equals 3.5 instead of M plus 2.8. So C equals 3.5, and I want to travel 20 miles. So, sorry, I said I apologize. That's going to be 70 plus 2.8. So it's going to cost me $72.80. Let's make sure I did it right. We're going to use a calculator. 3.5 times 20 equals 70, yeah. So notice I came out with that crazy answer before, and that told me to stop and reread the problem. When you get weird answers, make sure. So you have enough money to travel at most 20 miles in the taxi. Find the domain in range. Okay, so the domain in range, all right, well, let's go like this. Let's make it. This is hard. So my x-axis is going to be miles. And I know my max miles is going to be 20. And then my y-axis is going to be cost. in dollars. So if, watch this. If I travel 0 miles, do you know what my cost is going to start at? That's a trick question. Do you know what, if I have 0 miles, how much money is it going to cost me? Not zero. A lot of people would say, well, you haven't gone anywhere. But remember, it costs $2.80 to just get in the cab. So this is going to be your first data point. And then after 20 miles, it's going to cost you $72.80 after 20 miles. Now this is going to be continuous. It's not going to be discrete. It's going to be continuous because you can drive partial miles. You can drive a half mile and be charged at a partial cost. So that will look like this. So what is your domain and range? So we can derive that. So my domain is still going to be 0 m is less than or equal to 20, because that's the number of miles I can drive. And the range is going to be the tricky part. The range, not tricky, it's just you need to know that it's going to be $2.80 is greater than or less than or equal to C, which represents the cost, which is less than or equal to 20. So those are my costs, not 20, sorry, $72.80. $72.80. So that is the range of my how much I have to spend. Okay, that was kind of tricky, but a good one. You have enough money to travel at most 20 miles, find the domain and range. So those would be the domain and range. In exercises 11 and 12, sketch a graph of a function with the given characteristics. This is pretty cool. I love this problem. This problem is very, very, you want to show knowledge? This is a great question. The function is increasing when x is less than -6 and decreasing when x is greater than -6. So at -6, so 1, 2, 3, 4, 5, 6, at -6, it's going to be increasing to the left of -6, so it's going to be going up. And to the right of -6, it's going to be going down. So this is the point where the graph will change directions. And then that's the first part. So that's how I derived that first section. So it's going to be increasing up to here. It's going to be decreasing after -6. And that's this part of decreasing, increasing. Good. Now the function is negative. Negative means below the graph. It's below the graph when x is less than -8. So at -8, how do I do that? Let's do this. Let's get a different. So at -8, which is right here, it's going to be below the graph. Once it gets to the right of -8, it's going to go above the graph. So at -8, the function is negative less than -8, so it's going to be below here. So let's do red. So it's going to be below the graph at -8. Positive when x when x is greater than -8 and less than -4. So it's positive above that from -8 to -4. 1, 2, 3, 4. So from between here, it's going to be above the graph. So it's going to be going up, and then it's going to turn. And it's going to turn at -6. So that's important. And then let's do this. It's positive. Oh, it's negative. Why did I do green? It's negative there, and then it's positive between here, and then it's negative again when x is greater than -4. So at -4, it's going to go back below the graph. Okay, and so that looks like that. So if I had to draw it without all this noise, let's do this. I think, well, I think it's going to look like this. I don't mind. Let's do it in black. So I know the intercepts, haha, are -8 and -4. 1, 2, 3, 4. Those are my intercepts because that's where it goes from negative to positive. So I know that those 2 points are going to be zeros because it's neither positive nor negative. And then I know at -6, it's going to change its direction and it's going to be above. So I can do something like this, and then I can draw this. It's below. It's below. So there. I think that's what the graph looks like. Yeah, that's a fun one. All right. The linear function. The linear function, I think this is the last problem. It is. The linear function m equals 10 minus 1.44 represents the amount of m, the amount m in dollars of money that you have after printing P photographs. All right. So m represents money left. P is the number of photos. Negative 1.44 is the cost per photo, and I have $10 to spend. So that's, interpret the terms, the coefficients in the equation. So M is money left. 10 represents the amount I can spend, the amount I have or can spend. Negative 1.44 P represents the cost of my photographs, cost of photos. Photos, I don't know how many because I have P photos, and P represents the number of photos. All right, that's cool. Find the domain of the function. Is the domain discrete or continuous? Explain. So the domain of the function, all right, well, what's my formula? So m equals 10 minus 1.44, I think it's 44, p. So when I start plugging in for my independent, which is p, I can use this formula, 10 minus 1.44 p, and m is my dependent because m depends on p. So I'm going to have p comma m, photos, money, left over. So when I buy 0 photos, I'm going to have $10 left because I haven't spent any money. If I buy 1 photo, I'm going to have 10 minus 1.44, which is going to be 8.56. So 8.56. 2 is going to be 10 minus 2.88, which gives me 7.12. So 7.12. Oh, let's jump out to, I don't know, 5. Let's see, m equals 10 minus 1.44 times 5. 1.44 times 5 gives me 7.2. So that's 10 minus 7.2, which is 2.8. So $2.8, $2.80 left if I buy 5 photos. Let's do 10 photos. I know that's too much. No, let's do 9. Let's do 9. Let's at least get close. Or let's do 8. 8. I bet you 8's really close. 10 minus 1.44 times 8. That's going to be too much. So 1.44 times 8 gives me 1152. So what I wanted to show you, 1152, that gives me negative 152. So I'm over. I I've spent too much. I've spent more than $10. So 8 is negative 1.55. So that's a no bueno. I can't buy because I don't have enough money. I still owe $1.55. So we can do 7, but that's going to be 144. So I think it's 6. 6 is going to be my max. 10 minus 1.44 times 6. I could do that in my head, but we have a calculator and I want to go home. 864. 10 minus 864 gives me, gives me 1.36. So when I buy 6 photos, I have $1.36 left, and I don't have enough money because it costs $1.44. So I know I can't go to 7. All right, so this helps me with my question. Find the domain. So the domain is going to be 0, 1, 2, 3, 4, 5, 6. Why is it discrete? It's discrete because I can't buy half a photo. What do I just want the top end of the photo? No. 0, 1, 2, 3, 4, 5, 6. Graph the function using its domain. So we would need to plug in each of the points. We would go and we'd have photos. We have leftover money. Oh, that's kind of funky. We have leftover money. So at 0 photos, we would have $10. So that would be a point. And then down here, we would have 6. And we would not be at 0. We would be at, that would be a point right here, a discrete point, which would say 6, 1.36. We would need to remember that that y value represents the money left over. And then we would have dots at 1, 2, 3, 4, 5. So you'd have boom, 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 and it would be linear. I don't know what those values are. Cool. Whew. Hour and a half video. It's pretty long, but I think you understand. Good luck.